So my talk is going to be a little bit different from, I think, the major theme of today, since my background is not in quantum computing. But actually, I think it follows rather nicely from the previous one. In theory, I'm going to show some results of experiments in electronic nanodevices. But I think that in general, I want to raise a rather more general problem that should be relevant for the topic of this conference, which is implementation of quantum technologies. So in general, when we think about any device as in anything that performs any useful function, there is a connection between its function, what it actually does, and its structure in terms of what it's actually made of. In chemistry, since I now, for some reason, find myself in the Department of Chemistry, I found out this is called structure-property relations. And it's a topic of major research to find out how the structure of a molecule determines the properties of material in the macroscopic sense. However, when we talk about macroscopic devices, it may not be entirely trivial, as we can see from this picture, if we actually have a device to take it apart and figure out why it's doing what it's doing. But it's never really a topic of any scientific research, in the sense that if we have something that works and it's macroscopic, we usually know, or at least someone knows, why it does it and what's going on inside. However, when we move to smaller devices, this stops being necessarily the case and actually becomes a scientific problem. So since my background is in electronics, I'm going to give an example from electronics. So if you want to make a quantum dot, and you want to make a quantum dot by patterning metallic leads over 2D electron gas, as shown in the first picture from some recent paper of mine, then you pattern your metallic leads. You can perform microscopy, and you see that it's all been done correctly. You know where they are. You know what voltage you apply to your electrodes. And you know you can see the quantum dot in the center where the purple electrode supposedly is sitting. So you can actually see what's going on inside your device. If you want to go smaller, or in this case, not particularly smaller, but using a somewhat different technology, say you want to pattern a quantum dot out of graphene, where the quantum dot is that circular bit in the center of the next picture. Then one would think that I'm cutting out this circular bit out of graphene. This is going to be my quantum dot. And the constrictions around it are going to be the weak couplings to the larger electron baths. However, if you actually do it, it turns out that the size of the quantum dot doesn't typically depend really strongly on the size of this nice circular area that you cut out for it. In fact, it's typically quite a lot smaller, and sometimes you get 2 quantum dots. And the reason for that is that the electrons which actually occupy this quantum dot, or rather your device, don't care for the fact that you really made them a nice little quantum dot of the size that you want, and often find confined states on some defects in those narrow constrictions that you've made for them. And sometimes there are 2 defects, and you actually get a double quantum dot. Now, if we move even smaller and go to my background, which is molecular electronics, the whole idea or the selling point of molecular electronics is that by definition, all molecules of the same kind are absolutely identical. So if you could somehow design a molecule which performs some electrical function, say a molecule which acts as a transistor, then in theory, you'd get as many as you want of absolutely identical nanoscale transistors. Now, there are 2 issues with that. Issue number 1 is that if you look at this picture, you see that these things that we couple this molecule to are highly irregular and highly non-identical. So even if your molecules are identical, for now, we aren't able to connect them to absolutely identical electrodes. And the second issue that, yes, we are very good at chemical synthesis. And yes, we're very good at chemical characterization. But this is the only characterization of a free molecule. However, we don't know exactly how the properties of this molecule are going to change when we put it in a solid-state device. And it's pretty reasonable to assume that they're going to change quite a lot. So in a sense, what we're missing is essentially this connection, which I think is reasonable to all structure-property relations. The ability to actually understand what's going on inside the device after we made it. Because we can know, essentially, its efficiency if we want to think of this quantum dot or whatever as a heat engine, or, I don't know, what rectification ratio, whatever parameter we want to measure. But we actually also want to understand how exactly it manages to accomplish what it's done, if we actually want to develop anything and make improvements. So I'm going to give 2 examples from molecular electronics on actually trying to solve this problem. But I think it is a rather more general problem that for people trying to implement quantum technologies, it's important to think about. So I'm going to give a very short introduction to the physics of my kind of nanodevices for those who aren't familiar with it, but I think most people would be. So a nanodevice in my language is a small island quantum dot molecule or whatever thing sitting between 2 or more electron baths. The major energy scale is electrostatic, where if we talk about the electrostatic energy of this island, we have a square term with the number of electrons occupying it for the Coulomb repulsion of electrons on it. Then we have a linear term for the energy in the external potential of the gate, from which we can extract a full square. There's Ng, which you can see, which is a function of the gate voltage we apply, which is the non-integer number of electrons it wants to be. It wants to have on this quantum dot. And then we have n and n plus 1 around it, which are the 2 possible ones that it can take. And current happens through switches between n and n plus 1 in an expression where you can see where we have 4 rates for possible hops from n and n plus 1. Now if we look at what these rates are, they have the gamma t and gamma f to and from. There is a small gamma which corresponds to the geometric coupling factor, essentially how far they have to tunnel. There is the filling factor in the electron bath, which is how many electrons there are to tunnel in, if we are talking about tunneling in, or the number of available spaces to tunnel out if we're talking about tunneling out. And then there are these coefficients, which I call dn plus 1 and dn, which, if you think about them intuitively, what they are is, if in your n state, your quantum dot has 1 unpaired spin, as showed in this picture, then if we add another electron, there is a selection rule for how it can go in. It has to go in with the opposite spin. But if we want now to remove one, we can either remove the one that has just come in, or we can remove the one that was there before. So essentially, removing is twice easy. Like, there is no selection rule for removing, but there is a selection rule for going in, which means that going in is harder than going out, which means that the population of this quantum dot is lower than it would have otherwise if there was no degeneracy in the spin. And one can show either from the writing the Gibbs distribution formally or from the entropy grouping axiom or in many other ways that the population is dependent on entropy and is basically the Fermi distribution shifted by T delta S, which is an important thing. When I move to my first experimental example, we had an experiment where we had a molecule, I have no idea what that molecule is, but we're coupled to 2 gold electrodes. And each side of this device also had a heater. So a rather clever thing that I did not invent and that our experimentalists did was apply a constant bias between the electrodes, then a small oscillating fluctuation on top of it, and then a fluctuation of a different frequency to one of the heaters. And then what you can do is you can demodulate the current you get through this device at 0 frequency to get direct current. Then at the frequency of your small bias oscillation, which gives you differential conductance. And then at twice the frequency of your heater voltage, which gives you thermocurrent. So in principle, you can get a complete map of this. But what I'm going to look at is just the dependence of thermocurrent on gate voltage for different magnetic fields. As I said before, we know that population depends on entropy, we know that current through this thing depends on occupation probabilities, because to hop on, you have to have the quantum dot empty. To hop off it, you have to have it full. So the current depends on occupation, which in turn depends on entropy. So it is possible to write an expression for thermocurrent, which has entropy difference between the two available charge states explicitly. And now we can use this expression to fit our thermocurrent traces. And if you look at them carefully, at zero field, you can see that the first peak is higher than the second one is low. Then at around 6 Tesla, the trace is roughly symmetric. And then for 8 Tesla, you have the second peak, which is lower than the first one is high. And the clever thing, well, a convenient thing is that this delta S is the only important fitting parameter in our curve, because the other ones are the overall position of the curve and gate voltage, the overall amplitude, and the width depends on the temperature and also the lever arm. It doesn't really matter. So what you get is a data set that shows you the fitted entropy difference as a function of magnetic field. And now we go into a pretty interesting logical process where we look at this and try to essentially solve a puzzle, trying to figure out what could be going on in this molecule to give us this entropy difference. So if you look at zero field, you see minus logarithm of 2. There is some error bars, but they're not significant, and maybe, I don't know, maybe error is underestimated. So maybe it's exactly logarithm of 2. And if it was exactly minus logarithm of 2, it makes you think of doublet to singlet. But if it were doublet to singlet, then at higher field it would go to 0, because we would be only transitioning from the low energy singlet to the singlet in the higher charge state. But instead we cross 0 and go to positive entropies, which allows us to make the next guess and say that the next simplest solution is to add a triplet on top of the singlet. And if you do this, here comes the circular logic. It allows you to find an actual model for what the dependence of entropy on magnetic field should be, where the singlet-triplet splitting is a fitting parameter. So in principle, what happened here is that we were able to make a guess of the energy level structure of this thing, even with quantitative parameters of it, just from measuring some electrical property of the molecule. So in principle, it can be used theoretically to guess what's going on in your system without knowing anything about it, which has just been shown. It doesn't work very well when you have a more complicated molecule, even though people have been trying to use it for things like looking for Majorana fermions, which supposedly have strange entropy differences, such as logarithm 2 divided by 2. But another thing that is more practically useful for molecular electronics is get a molecule, find its energy level structure in the free state, then use it as our starting assumption as its energy level structure in a solid state device, and see how different quantities changed when we put it into the solid state. So this is example 1. If I have a little bit of time, I'll show you example 2. Do I have a little bit of time? Yes, I do have a little bit of time. So that everything before has been at 0 bias. If we go to larger biases, we can show that if we have a very large bias so that the thermal spreading of the Fermi distribution doesn't matter, and 2 opposite bias cases for the same device, then the logarithm of the ratio of this positive and negative current, in a very special case where one coupling is a lot stronger than the other, is equal to the entropy difference between the charge states. Now, why am I talking about this very special case where one coupling is a lot stronger than the other? It's because it is true in most of this kind of devices, mainly because if you have something in between 2 baths, it's usually not positioned exactly symmetrically. And since tunneling is exponentially dependent on the distance, it means that if your distances are slightly different, then the difference in coupling strengths is exponentially different. So this can be seen just so in picture 1, the current is limited through hopping on this quantum dot through the weak, as in thick, coupling. And on the second picture, the current will be limited by hopping off. So if you think about my previous case of hopping on and hopping off and two versions of one and one of the other, you can see that the current ratio would be 2 and the logarithm would be exactly the entropy difference. But it can be shown more rigorously from the fluctuation relation that we've seen in the previous presentation. Now if we look at what it actually looks like in a device, we had a current map shown there. If we correct for the tilt, which is the interplay between the bias voltage and the gate voltage, and plot the map of the logarithm of the ratios, we get the map below, which looks quite a lot sharper, which is an interesting feature of it. And also, if you plot some cuts, you can see that there are nice values on there, such as logarithm 4, logarithm 2, another logarithm 4, 0, which actually meant a 0 entropy difference. Which there was a slightly more complicated story that I don't think I have the time to fully explain about what happens in the selection rules. But in principle, what these values on this cut give us is that there is an entropy difference of logarithm 4 for adding one electron, and then an entropy difference of 0 for adding another one. But for adding another one, we can only go to 2 states from each one. It's maybe a bit confusing, but what I'm trying to explain is exactly this graph here, where logarithm 4 makes us think that there's a logarithm 2 from spin orientation, and then another 2 from 2 sides, which nicely agrees with the 0, because then when we add another one, there's still 4 states. And then this logarithm 2 there happens from the fact that from each one, we can go to only 2 of the 4 available in the next charge state. Which again allowed us to guess that we had a molecule, which was actually a triplet, but in fact, from the entropies that we could look at it, we can see that it actually acts as a doublet. And we can probably guess that that's because the actual sites where electrons sit are either one coupling with the electrode or the other, which was supported by DFT later, but I don't have a picture for that. And as a final image, some very recent experimental data that I've been sent like 2 weeks ago. Actually, I'm not entirely sure what it's on, but if anyone has ever worked with maps like this, you know that there is a special art in choosing a color scheme that would show your features that you want to see in a nicer way. So what I did instead was plot this logarithm of the ratio of the current, which, well, there were some interesting values, including logarithm of 2 and for some reason logarithm of 7. But you can see that without any attempt to recolor the thing, it still gives us features that we wouldn't be able to see in the original map. And now just to close the talk, I wanted to say that I wanted to raise this issue of trying to understand what's happening in your device when your device is so small that microscopy doesn't really do the trick. And that, well, I didn't show any new experiments. All the measurements that have been done are measurements that people are already routinely doing. The actual question was, how do we interpret the data that allows us not to just see the final result we want to see, such as efficiency, but that would highlight the features of this device that would allow us to understand what's actually going on inside it, which I think is a general, very interesting problem. And finally, I want to thank my experimental collaborators who sent me all this nice and somewhat mysterious data. And also Ronnie Koslov, who couldn't be here. I'm not entirely sure why, but he couldn't. But I suppose that he sends his best wishes to everyone who is here, and who is my host at the Hebrew University. And also the Israeli Foundation, who are funding my fellowship with Ronnie, which is very nice of them. Okay, and now I think it's time for questions.
Thank you for the talk, Eugenia.
Thank you for the talk, Eugenia. It was very interesting to know, although the experiments they're not so new. But I have a question. So, in your research, you can see, let's say, provided the expression for the current using its classical approach with probabilities and other components. So my question is to you, why do you consider quantum dot as a classical current, as a classical object? Because in principle, we can consider the classical regime where the current is given by like the Landau-Boutiquer approach or other quantum regimes.
Well, that connects to a more general question of what exactly is quantum and how do we get to it. Because I agree with the fact that nothing in this presentation has been quantum, even though I suppose that all my experimental collaborators would disagree with them, because for them, tunneling is already quantum. Currently, I'm working with Ronnie exactly on trying to extend the sort of standard master equation approach to exchange of both energy and particles, to see if we can use electronic measurements to do something more truly quantum. But I think that in most people's opinions, that would be quantum. For example, if we had an avoided, well, we didn't have a high enough field, but for example, we could have had an avoided crossing in the singlet and between the singlet and the triplet. Would you call that quantum, or already quantum enough to be quantum, or not, even though the current expression is kind of classical? So it's kind of a shifty place to be in.
Do we have another question?
Thank you for the talk. I have a general question. So what is the environment you're working in? Is it like vacuum, or do you put the molecule into some, I don't know, a solution, solvent?
So the way it usually works is that, well, everyone always asks how molecules are deposited. And the answer is kind of slightly embarrassing, because what people do is make, I don't know, 1,000 pairs of electrodes on each chip, and then just put a drop with these molecules on top, and see in which device you get something, you get a change in conductance, and then say that this is my device with the molecule. But after that, they just, essentially the molecule just stays, and all these measurements have been done at low temperatures, I think.
Okay.
I think the second one with the dimer was at nitrogen temperature, and the first one was 3.5 Kelvin.
The question I'm asking is just what would happen if you have also an environment around, and also to your spin? Is it like, then do you have some effects that it's like transferred to the environment, or that you get some, like, that this delta S is getting reduced?
There are proposals for using these molecular devices as sensors.
Yes.
So you essentially have a molecule, and a molecule is coupled, when it couples to electrodes, it couples really strongly, so it never like floats away.
No.
So it can sit in an environment in principle, and there are ideas of using it as a sensor where something comes to it.
Okay, but can you propose something in this direction, in this in your like spin measurements, and if you use it as a device?
As in the change of entropy of a sensor when yes, there's no reason why not.
Okay.
The only problem with it is that for this particular method, you need to take quite a lot of traces, as you saw. So if it is a sensor for something, this something would need to sit on the sensor for long enough for you to be able to take all these traces.